Hey guys, and welcome to this lesson video talking all about solving two-step equations. Now, up until now, all the equations we've seen have required only one step of addition, subtraction, or multiplication and division to solve. I don't know, we've dealt with things like m plus 7 equals negative 11, right? All we had to do was say, you know what, m is going to be 7 less than negative 11. We could subtract 7 from both sides of the equation, and we ended up with our solution of m equals negative 18. Everything is groovy. Or perhaps a multiplicative one-step equation in which perhaps negative 5/4 times m was equal to something like 20, in which case all we had to do was multiply both sides of the equation by the multiplicative inverse of this coefficient right there, in this case negative 4/5, and we would end up with a new equation in which, of course, these two multiply to 1. We'd end up with 1m equals, let's see, negative 16. And so our solution in that case was m equals negative 16. But note that both of these required just one step of either addition and subtraction or multiplication and division. So the equations that we're going to be learning about now are going to actually require two steps to solve. So let's take a look at our first one. 3 times b plus 5 equals 17. Now this is a nice and easy starting equation. Perhaps you can tell immediately what this number needs to be. And indeed, yes, b is going to have to equal 4, because 3 times 4 plus 5 does indeed equal 17. So yes, we already know what the solution is going to be. Our solution to this equation is 4. But I want to think about how you may have done that intuitively. I bet what you did is you thought, well, 3 times b has to equal 12, right? 5 less than 17. And in fact, that's exactly how I would suggest starting this type of an equation, by subtracting 5 from both sides of the equation and ending up with a new simpler equation, 3b equals 12, that we can then multiply both sides of that equation by 1/3, yielding exactly what we thought we'd end up with, that b equals 4, the eventual solution to this equation. Now I chose this simpler one to begin because I think we could do it intuitively, but this is the general strategy when you have a two-step equation that you need to solve, right? Here we have 3b, and if it were just 3b equals something else, we're good to go, everything's groovy. But we have this additional step of kind of interaction or manipulation going on with this variable. So we kind of want to peel back the layers, if you will, so we can access that b and isolate it. First, we want to subtract this 5 in this case. So we have just 3b equals 12, and then divide both sides by 3 or multiply both sides by 1/3 to finally isolate our unknown variable. And that's going to be the general strategy. Let's do a couple more. So in the second example, in the second example, we have 5 is equal to 4 times m minus 3. Well, I want to kind of peel back the layers and get at this variable m here. So how are we going to do that? The first thing I do is add 3 to both sides of this equation. So we'll just have a 4m hanging out on one side. You can also use intuition and say, listen, if 4m minus 3 equals 5, this quantity right here, 4m, has got to be equal to 8. So we're using intuition as well as some formal notation here. So now we have 8 equals 4 times m. I think we know what to do from here. Let's multiply both sides of our equation by 1/4, and we end up with 2 equaling m, the solution to that original equation. Let's check to make sure. 4 times 2 is 8, 8 minus 3 is 5. And so this is the general gist of how to do a two-step multiplicative equation in which our variable, or some multiple of that variable, is not yet isolated. We just have to do one step to isolate it and take it from there. All right, so I think we're going to make our way on to slightly more complicated examples. I do want to make a note in this case that there is a potential pitfall that sometimes students do. So I want to bring that to your attention. You know, in this particular example, 2 times w plus 6 equals 12. The first thing I would do is subtract 6 from both sides of the equation, yielding 2w equals 6. Then I would multiply both sides of this equation by 1/2 to isolate just one of those w's, and we end up with w equals 3. And life is good. So this is the way that I kind of prefer. I like to isolate a multiple of our variable and then just take it from there, one step of multiplication. So the first thing I like to do is subtract 6 in this case. There is another strategy you can take. I don't advise it as much, but I at least want to show it to you. A lot of students sometimes focus in on this 2 times w and they think, aha, eventually I'm going to want to divide by 2 or multiply by 1/2 in order to get just 1w, to isolate this unknown variable. That's groovy. But note to self, on the left-hand side of this equation is a number. 2w plus 6 is a number. 12 is also a number. And if you're going to multiply the right-hand side of this equation, that number, by 1/2, you must multiply the entire left side of this equation by a half, which will yield, I hope you know, 1W plus 3 equals 6. And from there, it should be no surprise that indeed our solution is, again, W equals 3. We got the exact same solution as we did before, but instead, in this second example, we multiply both sides of the equation by a half to begin with. Some students aren't really into the multiplying by a half. They prefer to divide by 2, which is the same thing, and they do one of these. That's fine. You just really got to make sure to know that if you are going to divide or multiply both sides of an equation by a number, you must multiply the entire side or divide the entire side by that number, every term on each side of the equation. So in this case, you're dividing both 2W by 2 and 6 by 2. It's like 2 apples and 6 oranges. If we cut that in half, it's 1 apple and 3 oranges. So what you wouldn't want to do not do this. Oh, breaks my heart when I see this. I see divided by 2, and the student will write 1W plus 6. They forget to divide 6 by 2, and you get an obviously nonsensical statement. W equals 0 is certainly not the solution to this equation right here. So just wanted to put that potential pitfall on your radar. Now note, okay, sometimes we're going to have some nasty fractions involved with our equations, and that's totally fine. Let's handle this in exactly the same way that we would before. I see that I've got some multiple of k hanging out here, but there's a little bit more going on, another interaction with another number. Let's peel back the layers. Let's first add 3 to both sides of this equation, and we end up with negative 5/7 times k is equal to 15. I think we're in a position now to multiply both sides of the equation by the multiplicative inverse of that number, namely negative 7/5. Awesome. We know that negative 7/5 multiplied by negative 5/7 will yield us 1. So we've got 1k equals, let's see, 15 times negative 7/5. A little simplifying. I think it's going to be negative 21. So our solution in this case is that k equals negative 21. Phenomenal. Some students like to take a slightly different route, which involves what I would call clearing fractions. And clearing fractions means, we have a fraction here, and we've got 2 integers here as well. And you know what? Fractions and integers just don't always play so well together. So what we like to do is we like to create a new equation in which there are no fractions at all. And one way to do that is as such. What I kind of first do is I write all of the terms as fractions, all having 7 as their denominator. So I might write this as negative 21 over 7 minus 5/7 times k equals 84 over 7. And now that we have all of these kind of fractions with 7 as their denominator, you can multiply both sides of the equation by 7. And I hope you can tell that there's going to be a lot of easy simplifying. Right? This 7 and this 7, it's going to simplify to 1, right? Because 7 times this, I'll even say cancel the 7s. 7 times this number, you can cancel the 7s. 7 times this number, you can even cancel the 7s. And we end up with just negative 21 minus 5 times k equals 84. Wow, not so bad at all. Not so bad at all. And that's actually what you'd get if you multiplied both sides of our original equation by 7. So that's an option if you'd like to use it. And from here, we are just going to add 21, negative 5 times k is equal to 105. If we multiply both sides of this equation by negative 1/5, we end up with the solution, k equals negative 21. Is that the exact same number that we had before? Indeed it is. Indeed it is. So I wanted to introduce you to this idea of clearing fractions when an equation has a lot of fractions in it. Now,